So hello everyone and welcome to NEETOPEDIA, that is NEET ka Encyclopedia, and we are back with our chemistry audiobooks. In the previous audiobook, we had already finished through group 16 elements, that was Halogens, and today we'll be starting with group 17 elements. Please note that the audiobook of P block elements from group 13 to 18 is group wise, that is 13, 14, 15 and so on. And today we'll be starting with group 17 elements. So without wasting our time, let's get started. 7.18 Group 17 elements. Fluorine, chlorine, bromine, iodine, astatine and tungsten are members of group 17. They are collectively known as halogens, that is, salt producers. The halogens are highly reactive non-metallic elements. Like groups 1 and 2, elements of group 17 show great similarity amongst themselves. That much similarity is not found in the elements of other groups of the periodic table. Also, there is a regular gradation in their physical and chemical properties. Astatine and tungsten are radioactive elements. 7.18.1 Occurrence. Fluorine and chlorine are fairly abundant while bromine and iodine less so. Fluorine is present mainly in insoluble fluorides, cryolite and fluorapatite. A small quantities are also present in soil, river water, plant and bones and teeth of animals. Seawater contains chlorides, bromides and iodides of potassium, sodium, magnesium and calcium, but it is mainly sodium chloride solution. The deposits of dried up sea contains these compounds, that is sodium chloride and carnallite. Certain forms of marine life contain iodine in their systems. Various seaweeds, for example, contain up to 0.5% of iodine, and child saltpetre contains up to 0.2% of sodium iodate. Here, important atomic and physical properties of group 17 elements other than tungsten are given along with their electronic configurations. Tungsten is a radioactive element. Its symbol is Ts and atomic number 117. Atomic mass 294 and electronic configuration is Radii 5f14 6010 7s2 7p5. Only very small amount of element could be prepared. Also, its half-life is milliseconds only. That is why its chemistry could not be established. The trends of some of the atomic, physical and chemical properties are discussed below. 7.18.2 Electronic configuration. All these elements have 7 electrons in the outermost shell, which is 1 electron short of the next noble gas. 7.18.3 Atomic and ionic radii. Halogens have smallest atomic radii in the respective period due to maximum effective nuclear charge. The atomic radius of fluorine, like other elements of second period, is extremely small. Atomic and ionic radii increase from fluorine to iodine due to increasing number of quantum shells. 7.18.4 Ionization Enthalpy. They have little tendency to lose electron. Thus, they have very high ionization enthalpy. Due to increase in atomic size, ionization enthalpy decreases down the group. 7.18.5 Electron gain enthalpy. Halogens have maximum negative electron gain enthalpy in the corresponding period. It is due to this fact that atoms of these elements have only 1 electron less than the stable noble gas configurations. Electron gain enthalpy of the elements of the group becomes less negative down the group. However, the negative electron gain enthalpy of fluorine is less than that of chlorine. This is due to the small size of fluorine atom. As a result, there are strong interelectronic repulsions in the relatively small 2p orbitals of fluorine, and thus the incoming electron does not experience much attraction. 7.18.6 Electronegativity. They have very high electronegativity. The electronegativity decreases down the group. Fluorine is the most electronegative element in the periodic table. Example 7.14. Halogens have maximum electronic gain enthalpy in the respective periods of the periodic table. Why? Solution. Halogens have the smallest size in the respective period and therefore high effective nuclear charge. As a consequence, they readily accept 1 electron to acquire noble gas electronic configuration. 7.18.7 Physical properties. Halogens display smooth variations in their physical properties. Fluorine and chlorine are gases, bromine is a liquid and iodine is a solid. The melting and boiling points steadily increase with the atomic number. All the halogens are colored. This is due to the absorption of radiations in visible region, which results in excitation of the outer electrons to higher energy level. By absorbing different quanta of radiation, they display different colors. For example, F2 has yellow, Cl2 has greening yellow, Br2 red and I2 violet color. Fluorine and chlorine react with water. Bromine and iodine are only sparingly soluble in water but are soluble in various organic solvents such as chloroform, carbon tetrachloride, carbon disulfide and hydrocarbons to give colored solutions. One curious anomaly we noticed from table 7.8 is the smaller enthalpy of dissociation of F2 compared to that of Cl2, whereas XX bond dissociation enthalpies from chlorine onwards show the respected trend as ClCl is greater than Br is greater than II. A reason for this anomaly is the relatively large electron-electron repulsion among the lone pairs in F2 molecule, where they are much closer to each other than in the case of Cl2. Example 7.15. Although electron gain enthalpy of fluorine is less negative as compared to chlorine, fluorine is a stronger oxidizing agent than chlorine. Why? Solution. It is due to number 1, low enthalpy of dissociation of FF bond, number 2, high hydration enthalpy of F- ion. 7.18.8 Chemical properties. Oxidation states and trends in chemical reactivity. All the halogens exhibit -1 oxidation state. However, chlorine, bromine and iodine exhibit +1, +3, +5 and +7 oxidation states also, as explained below. The higher oxidation states of chlorine, bromine and iodine are realized mainly when the halogens in the combination with small and highly negative electronegative fluorine and oxygen atoms. Example in interhalogens, oxides and oxoacids. The oxidation states of +4 and +3 occur in the oxides and oxoacids of chlorine and bromine. The fluorine atom has no d orbital in its valence shell and therefore cannot expand its octet. Being the most electronegative, it exhibits only -1 oxidation states. All the halogens are highly reactive. They react with metals and nonmetals to form halides. The reactivity of halogens decreases down the group. The ready acceptance of an electron is the reason for the strong oxidizing nature of halogens. F2 is the strongest oxidizing halogen and it oxidizes other halide ions in solution or even in the solid phase. In general, a halogen oxide oxidizes halide ions of higher atomic number. The decreasing oxidizing ability of the halogens in the aqueous solution down the group is evident from the standard electron potentials, which are dependent on the parameters indicated below. The relative oxidizing power of halogens can be further illustrated by the reactions with water. Fluorine oxidizes water to oxygen, whereas chlorine and bromine react with water to form corresponding hydrohalic and hypohalous acids. The reaction of fluorine with water is non-spontaneous. In fact, I- can be oxidized by oxygen in acidic medium, just the reverse of the reaction observed with fluorine. Anomalous behavior of fluorine. Like other elements of the p block present in second period of the periodic table, fluorine is anomalous in many properties. For example, ionization enthalpy, electronegativity and electrode potential are all higher for fluorine than expected from the trends set by halogens. Also, ionic and covalent radii, melting point, boiling point, enthalpy of bond dissociation and electron gain enthalpy are quite lower than expected. The anomalous behavior of fluorine is due to its small size, high electronegativity, low FF bond dissociation enthalpy, and non-availability of d orbitals in the valence shell. Most of the reactions of fluorine are exothermic due to small size and strong bond formed by it with other elements. It forms only one oxoacids while other halogens forms a number of oxoacids. Hydrogen fluoride is a liquid due to strong hydrogen bonding. Hydrogen bond is formed in HF due to small size and high electronegativity of fluorine. Other hydrogen halides which have bigger size and less electronegativity are gases. Number 1. Reactivity towards hydrogen. They all react with hydrogen to give hydrogen halides, but affinity for hydrogen decreases from fluorine to iodine. Hydrogen halides dissolve in water to form hydrohalic acids. Some of the properties of hydrogen halides are given in table 7.9. The acidic strength of these halides varies in the order as HF is less than HCl is less than HBr is less than HI. The stability of these halides decreases down the group due to decrease in the bond dissociation enthalpy in the order HF is greater than HCl is greater than HBr is greater than HI. Number 2, reactivity towards oxygen. Halogens form many oxides with oxygen, but most of them are unstable. Fluorine forms two oxides OF2 and O2F2. However, only OF2 is thermally stable at 298 Kelvin. These oxides are essentially oxygen fluorides because of the higher electronegativity of fluorine than oxygen. Both are strong fluorinating agents. O2F2 oxidizes plutonium to PuF6, and the reaction is used in removing plutonium as PuF6 from spent nuclear fuel. Chlorine, bromine and iodine form oxides in which the oxidation states of these halogens range from +1 to +7. The combination of kinetic and thermodynamic factors lead to the generally decreasing order of stability of oxides formed by halogens. I is greater than Cr is greater than Br. Higher stability of oxides of iodine is due to the greater polarizability of the bond between iodine and oxygen. In the case of chlorine, multiple bond between chlorine and oxygen takes place due to availability of d orbitals. This leads to the increase in stability. Bromine attacks both the characteristics, hence stability of oxides of bromine is least. The higher oxides of halogen tend to be more stable than the lower ones. Chlorine oxides Cl2O, ClO2, Cl2O6 and Cl2O7 are highly reactive oxidizing agents and tend to explode. ClO2 is used as a bleaching agent for paper pulp and textiles and in water treatment. The bromine oxides Br2O, BrO2, BrO3 are least stable halogen oxides and exist only at low temperatures. They are very powerful oxidizing agents. The iodine oxides I2O4, I2O5, I2O7 are insoluble solids and decompose on heating. I2O5 is a very good oxidizing agent and is used in estimation of carbon monoxide. Number 3, reactivity towards metals. Halogens react with metals to form metal halides. For example, bromine reacts with magnesium to give magnesium bromide. The ionic character of halides decreases in the order Mf is greater than Mcl is greater than Mbr is greater than Mi, where M is a monovalent metal. If a metal exhibits more than one oxidation states, the halides in higher oxidation state will be more covalent than the one in lower oxidation state. For example, SnCl4, PbCl4, SbCl5 and UF6 are more covalent than SnCl2, PbCl2, SbCl3 and UF4 respectively. Number 4. Reactivity of halogens towards other halogens. Halogens combine amongst themselves to form number of compounds known as interhalogens of types XX-, XX-3, XX-5, XX-7 and X is a larger size halogen and X- is a smaller size halogen. Example 7.16. Fluorine exhibits only -1 oxidation states, whereas other halogens exhibit +1, +3, +5 and +7 oxidation states also explained. Solution: fluorine is the most electronegative element and cannot exhibit any positive oxidation state. Other halogens have d orbitals and therefore can expand their octets and show +1, +3, +5 and +7 oxidation states also. I'm skipping the in-text questions for you to solve it later, or you can pause the video and solve it right now. 7.19 Chlorine. Chlorine was discovered in 1774 by Shell and the action of HCl on MnO2. In 1810, Davy established its elementary nature and suggested the name chlorine on account of its color. Preparation. It can be prepared by any one of the following methods. Number 1. By heating manganese dioxide with concentrated hydrochloric acid. However, the mixture of common salt and concentrated H2SO4 is used in place of HCl. Number 2. By action of HCl on potassium permanganate. Manufacture of chlorine. Number 1. Deacon's process. By oxidation of hydrogen chloride gas by atmospheric oxygen in the presence of CuCl2 at 723 Kelvin. Number 2. Electrolytic process. Chlorine is obtained by the electrolysis of brine, that is concentrated NaCl solution. Chlorine is liberated at anode. It is also obtained by a byproduct in many chemical industries. Properties. It is a greenish yellow gas with a pungent and suffocating odor. It is about 2 to 5 times heavier than air. It can be liquefied easily into greenish yellow liquid which boils at 239 Kelvin. It is soluble in water. Chlorine reacts with a number of metals and nonmetals to form chlorides. It has a great affinity for hydrogen. It reacts with compounds containing hydrogen to form HCl. With cold and dilute alkalis, chlorine produces a mixture of chloride and hyperchloride, but with hot and concentrated alkalis, it gives chloride and chloride. With dry slaked lime, it gives bleaching powder. The composition of bleaching powder is CaOCl whole twice dot CaCl2 dot CaOH whole twice dot 2H2. Chlorine reacts with hydrocarbons and gives substitution products with saturated hydrocarbons and additional products with unsaturated hydrocarbons. Chlorine water on standing loses yellow color due to the formation of HCl and HOCl. Hyperchlorous acid, that is HOCl, so formed gives nascent oxygen, which is responsible for oxidizing and bleaching properties of chlorine. Chlorine oxidizes ferrous to ferric and sulfite to sulfate. Chlorine oxidizes sulfur dioxide to sulfur trioxide and iodine to iodate. In the presence of water, they form sulfuric acid and iodic acid respectively. Chlorine is a powerful bleaching agent. Bleaching action is due to oxidation. It bleaches vegetable or organic matter in the presence of moisture. Bleaching effect of chlorine is permanent. Uses. It is used for number 1, for bleaching wood pulp required in the manufacture of paper and rayon, bleaching cotton and textiles. Number 2, in extraction of gold and platinum. Number 3, in the manufacture of dyes, drugs and organic compounds such as CCl4, CHCl3, DDT, refrigerants, etc. Number 4, in sterilizing drinking water. Number 5, preparation of poisonous gases such as phosgene, tear gas, mustard gas. Example 7.17. Write the balanced chemical equation for the reaction of Cl2 with hot and concentrated NaOH. Is this reaction a disproportionation reaction? Justify. Solution: 3Cl2 plus 6NaOH gives 5NaCl plus NaClO3 plus 3H2O. Yes, chlorine from 0 oxidation state is changed to -1 and +5 oxidation states. So it is a disproportionation reaction. 7.20 Hydrogen chloride. Glauber prepared this acid in 1648 by heating common salt with concentrated sulfuric acid. Davy in 1810 showed that it is a compound of hydrogen and chlorine. Preparation. In a laboratory, it is prepared by heating sodium chloride with concentrated sulfuric acid. HCl gas can be dried by passing through concentrated sulfuric acid. Properties. It is a colorless and pungent smelling gas. It is easily liquefied into colorless liquid and freezes to a white crystalline solid. It is extremely soluble in water and ionizes. Its aqueous solution is called hydrochloric acid. High value of dissociation constant indicates that it is a strong acid in water. It reacts with ammonia and gives white fumes of NH4Cl. When 3 parts of concentrated HCl and 1 part of concentrated HNO3 are mixed, aqua regia is formed, which is used for dissolving noble metals like gold and platinum. Hydrochloric acid decomposes salts of weaker acid, example carbonates, hydrogen carbonates, sulfites, etc. Uses. It is used in number 1, manufacture of chlorine, NH4Cl and glucose. Number 2, for extraction of glue from bones and purifying bone black. Number 3, in medicine and as a laboratory reagent. Example 7.18, when HCl reacts with finely divided iron, it forms ferrous chloride and not ferric chloride. Why? Solution, its reaction with iron produces hydrogen. The liberation of hydrogen prevents formation of ferric chloride. 7.21 Oxoacids of halogens. Due to high electronegativity and small size, fluorine forms only one oxoacid, that is HOF, known as fluoric acid or hypofluorous acid. The other halogens form several oxoacids. Most of them cannot be isolated in pure state. They are stable only in an aqueous solution or in the form of their salts. The oxoacids of halogen are given in table 7.10 and their structures are given in figure 7.8. 7.22 Interhalogen compounds. When 2 different halogens react with each other, interhalogen compounds are formed. They can be assigned general compositions as of XX-, XX-3, XX-5, XX-7, where X is the halogen of larger size and X- of smaller size. X is more electropositive than X-. As the ratio between radii of X and X- increases, the number of atoms per molecule also increases. Thus, iodine fluoride should have maximum number of atoms as the ratio of radii between I and F should be maximum. That is why the formula is IF7. Preparation. The interhalogen compounds can be prepared by direct combination or by the action of halogen on lower interhalogen compounds. The product formed depends on some specific conditions. Properties. Some properties of interhalogen compounds are given in table 7.11. These are all covalent molecules and are diamagnetic in nature. They are volatile solids or liquids at 298 Kelvin except ClF, which is a gas. The physical properties are intermediate between those of constituent halogens except that their melting point and boiling point are little higher than expected. The chemical reactions can be compared with the individual halogens. In general, interhalogen compounds are more reactive than halogens except fluorine. This is because XX- bond in the interhalogens is weaker than the XX bond in the halogens except FF bond. All these undergo hydrolysis, giving halide ion derived from the smaller halogen and hypohalite, halite, halate and perhalate ion derived from the larger halogen. The molecular structures are very interesting, which can be explained on the basis of Vesper theory. The XX3 compounds have T shape and XX5 compounds have squared pyramidal and IF7 has pentagonal bipyramidal structures. Example 7.19 discuss the molecular shape of BRF3 on the basis of Vesper theory. Solution. The central atom Br has 7 electrons in the valence shell. 3 of these will form electron pair bonds with 3 fluorine atoms, leaving behind the 4 electrons. Thus, there are 3 bond pairs and 2 lone pairs. According to the Vesper theory, this will occupy the corners of the trigonal bipyramidal. The 2 lone pairs will occupy the equatorial positions to minimize the lone pair and the bond pair repulsions, which are greater than the bond pair repulsions. In addition, the axial fluorine atom will be bent towards the equatorial fluorine, and in order to minimize the lone pair repulsion, the shape that would be of slightly bent T. Uses. These compounds can be used as non-aqueous solvents. Interhalogen compounds are very useful fluorinating agents. ClF3, BrF3 are used for the production of UF6 in enrichment of uranium-235. So that's it for today. We'll continue the audiobook with group 18 elements further on in the next video. Till then, subscribe to the channel and stay tuned. Also, do not forget to check out the other NCERT audiobooks of physics, chemistry and biology on this channel. Till then, see you again. Thank you.